Okay, so the last video we kind of ended with these common cross sections, but you know AP, you know sometimes they like to ask you a curveball, so I want you to make sure that you're prepared for anything. What I'm going to do is actually work out the problem to what you see in this image. So I'm going to label this part A, and I just have the words to go along with this image. So of course you can stop this video wherever you want to and look at it, but I kind of wrote it out. This is sort of what it would look like. Let R be the region bounded by the graphs of y equals x squared, the x-axis, and the line x equals 2. They could ask you for area. They could ask you for a volume of revolution. But right now we're focusing on the volume of the solid with a known cross section. So for part A, what you see in that image, what appears to me is cross sections perpendicular to the x-axis. They have to be clear about where they are taking those cross sections from and what shape it is. So it's squares. So I want you to think about that and really think, okay, I'm going to find the volume. There's no spinning. It's basically the area of a square. And I'm going to think about this region and decide like, well, let me see if it's a dx or a dy. Let me redraw the shape in here. So I'm going to draw a couple of things. We have our graph of y equals x squared. We have x equals 2. We have the x-axis. You're still shading a region. And you're still going to draw a rectangle in the shaded region. You're going to draw it exactly the way that they told you to draw it, which is perpendicular to the x-axis. And that is the only way to draw it. So you can imagine the cross sections being squared, sort of jumping out at this image at you. However you want to view that is up to you. But I clearly see that I have a vertical rectangle drawn in. That means my integral is dx, end of story. That also tells me I get my limits of integration along the x-axis, end of story. The only thing I have to decide is, what's the area of a square? So I'm going to look at that rectangle, and I'm going to look at that kind of length there as being the side. So I'm going to write the volume, the integral from 0 to 2. I'm going to say, hey, if I could just find an expression for that side and square it, I'm done. There's no pi, there's no spinning. So I'm going to think about that side length in this example being, well, top minus bottom, because it's a vertical rectangle. That would be the top y coordinate. That's any xy ordered pair that's on that curve, minus the y coordinate of 0. That's consistent. When I put it in the integral, it has to be in terms of x, so I will pull that switcheroo move. Instead of saying y minus 0, I'm going to say x squared minus 0. Of course, you don't need the minus 0 in there, but this is your volume formula. This is set up. This is ready to go. If they asked you for the setup line, you've got it. Move on to the next problem. If they actually asked you to find the volume, then you would evaluate it. And I'm pretty sure, I'm confident everybody in here can definitely get this cranked out. That would be 1/5, x to the 5th, evaluating at 2 and 0, of course, and that is 32/5. That's your volume. Okay, so what I want to do is sort of change gears slightly and just what if I had the same region of my solid? What if my cross sections, I'll call this part B, what if your cross sections were perpendicular to the y-axis? And your cross sections are still squares. I'm not changing much about this, but I am going to change the orientation here, and I will get a different value. It's a different solid. I'm still talking about y equals x squared. I'm still talking about a boundary at x equals 2. But now my cross sections are perpendicular to the y-axis. So I'm going to draw what perpendicular to the y-axis looks like. Of course, I'm only going to draw that rectangle in the shaded region. And I'm going to mimic the same thing that we had done before. That I'm going to kind of imagine like, well, I definitely have these squares. You can see them in any orientation that you want to, sort of jumping out at you. But I'm going to set up the volume. And the volume is going to be exactly what we talked about over here. It's going to be the integral of the area of a square. The only thing that's changing in this case is I've got a dy. That is a horizontally drawn rectangle. And so I'm going to throw it in right now. My limits of integration are on the y-axis. So that bottom location will be y equals 0. The top moment there, remember if x is 2, y is 4. See how your limits of integration change. Now, I'm also going to work on that idea of the side length. Okay, the length of that rectangle is what I'm calling the side. So your formula for the volume is basically, well, the area of a square, which is nothing more than the side squared. So if I go over to this image and say, okay, what's side? Well, that's a horizontally drawn rectangle. That's going to be right minus left, of course. And that's really the x-coordinate of 2 minus some random x-coordinate that's on that curve of y equals x squared. In my integral, I definitely have to have y variables in here. It's clearly marked as a dy. So I'm going to make sure that I can make that work for myself. The equation here is y equals x squared. So I am going to solve this thing for x. Algebra tells me I have 2 possible solutions. If I am in quadrant 1, all y coordinates are positive. And so this is what I would get. Here's my volume formula based on changing the cross-section to now be perpendicular to the y-axis.